Okay, welcome to my back garden. I want to use this setup to illustrate some of the ideas behind a differential equation. What we've got in the setup is a bicycle stand holding a broom, from which we've got a scales that is using a mass that I've fixed in place. So normally you would move the mass up and down to measure the weights. And here on the end, I've got a flag. The idea is, as this bucket gets heavier, as I push down, the flag goes up. So this flag is measuring how much water is in the bucket. To put more water in the bucket, I can turn this tap on. So water will flow down the hose into the bucket. Now I need to point out to my children that yes, this used to be on the bucket, was almost falling off. The bucket itself used to have a little watering attachment for helping watering the garden, but perished through, so now there's just a hole at the bottom of the bucket. And the point about that hole is that the water flows out of the hole at a rate that's dependent on the pressure in the bucket. So the more water there is in the bucket, the faster the water flows out of the hole. So differential equations are, in a first order case, about flow. So I've got two types of flow going on here. I can control the inward flow by opening this tap. And for the purposes of my inaugural lecture, that's the function we're potentially interested in. How far have I got this tap open? But we don't observe that. So in the transcription factor example coming up later, that's the concentration of transcription factor activity, which is difficult to observe. And what we do observe is this flag here. So I can put water into the bucket by opening the flow, and water will emerge from the bucket at a rate proportional to how much, approximately, to how much water there is in the bucket. So the key thing is we're interested in the amount of water in the bucket, which is the gene expression level, and I can control that by changing the flow input into the bucket. So I'm going to start the system now by adding water to the bucket. So I'm turning the water on. As you can see, as the water increases, it starts to emerge, and it's going into a second bucket below. As a result, the amount of water in the bucket goes up. Now if I turn the water off, it's off now. After a period of time, the water in the bucket starts to drop because of the amount of water that's flowing out. Now that's the interesting characteristic of the equation as I've set it up. I'm opening up the tap again now, and shortly after I open the tap, the flag goes up, I close the tap, and once I close the tap, later the flag goes down. So depending on various factors, which includes the proportion of flow into this bucket, the proportion coming out of that hole, the size of that hole at the bottom, the delay between when I open the tap and when the flag moves can vary. So as I leave the tap closed, I closed it some time ago, but the flag continues to drop and the water continues to empty. If I open it now, there's a delay between me opening it and the flag rising. So I've stopped opening it, and only now is the flag rising. I see my hand away. And I can close the tap. It's closed it now, and now the flag drops. So that's very characteristic of the first order differential equations that we've been interested in. And in the sort of work we've been doing, this is the easy thing to measure, and where my hand on the tap is the difficult thing. So if you can't observe my hand on the tap, you have to infer what my hand was doing by just observing the flag. You also have to infer what the size of the hole is. You don't get to see that. So here you can actually see the flow rate out of the bucket. You wouldn't get to see that in the sort of bodies we're interested in as well. You have to infer that as well. So learning that in those systems is the challenge, one of the challenges. Very interesting. Okay, there it is. My simple model of transcription factor to gene expression in the back of my graph.